Hello everyone, welcome to it's not math. Welcome to CWI, Connecting with Ideas 101. What are the chances? Let's see, I'm going to share a blank whiteboard and we're going to write some stuff today. So here we go. First off, let's just do a little bit of a review. This is a review of the video that you watched recently on probability. So here's the idea of probability. And this is a little recap. Reviews are very, very valuable. The probability of some event A is always a fraction. So that's easy to set up. In the numerator on the top of the fraction, we have number of ways A could happen. And in the denominator, we have the number of ways anything could happen. So there you go, always a fraction. And that will bring us to our first law of probability. First law of probability is that the probability of something, since it's a fraction, will always be between, so less than or equals, it'll be between 0 and 1. And this is kind of a fancy mathy way of saying that there's a probability and it's bigger than 0. It could be 0 if it's an impossible event. If the likelihood of something occurring is 0, it just won't happen at all. That's possible. And if something's guaranteed, if something is a certain event, it could be 1. But usually they're in between there. And we had some examples in our video. If you're flipping a coin, what's the probability that you come up with heads? Well, it's 1/2, and you can see, oh yeah, 1/2 definitely between 0 and 1. If you turn things into percents, then sometimes they look like they're bigger than 1, right? A 0.5, a 1/2 probability is the same as 50%. This guaranteed event, the 1 in percents, is 100%. And if you are comfortable switching back and forth between percents like that, great. And if you're not, it's not a requirement for this class. For us, all we have to do is think that probabilities are always friends, and that's our first law of probability. The second law of probability then, and this one looks a little bit mathy. The second law of probability is that the probability of the sample space is 1. Let me write that out. So I had a second video on probability that explained how you can do probability without higher math. And what I said there was you don't have to use sets. And here I kind of am going back on that and using sets. So the idea of this S is the sample space, and that means all the things that are possible. And so that's really the denominator of this fraction, the number of ways anything could happen. So for example, in flipping a coin, our sample space is, well, it could come up heads or it could come up tails. And the probability of it doing one of those things is you're guaranteed. It's either going to come up heads or it's going to come up tails. And that's all this says, is that everything that's possible put together has a 100% probability of occurring. So we had an example of a non-theoretical probability, one in which the different outcomes have different likelihoods. That was weather, right? In Idaho, it's much more likely that it's a sunny day than it is that there's a tornado, right? We don't have very many tornadoes in Idaho. And so there are different probabilities. But if you put all of the possibilities together, rain, snow, sun, cloudy, windy, whatever it is, it adds up to 1. And kind of what we're saying there is, yeah, there's going to be weather. You're 100% assured that there's going to be weather. So those are our first two laws of probability. I'm going to spread these out over this lecture, and so I'll give you some study advice. This will be useful not only in this class for this particular lecture, but in other classes when you're learning things. There will be lots and lots of times where you learn stuff and it's spread out like this, sometimes over one lecture, sometimes over several lectures, depending on what you're learning. But in a certain sense, the material goes together. So here are 5 laws of probability, and I've given you 2. It'll be 10 or 15 minutes before you get the third one. We have to talk about things. So it will be somewhere else in your notes. And so in a situation like that, what I encourage you to do is do what your textbooks do. Your textbooks often have a summary page. The math books especially, I'm of course a math professor, so I'm the most well acquainted with those. In the very back of the math textbook, there's a review sheet, there's a formula sheet. And here are all these things about, say, trigonometric identities, and they're all put together on one page, half a page. And it's nice to have a reference like this. And so you can create your own. And when you're learning things, you learn this and you put it in your notes because this is where it comes. And then the professor talks about something else and it comes. And then there's 10 or 15 minutes. And so a couple pages later in your notes is number 3. Well, what you can do is in the very, very back of your notebook, if you have one of those spiral notebooks, or if you have a 3-ring, you can organize it how you like. But when I was a student, what I would typically do in the very back of my spiral notebook is I would put my little formula sheets. I would have little summaries. And so in this class, if I'm teaching face-to-face, what I do is I present everything on a whiteboard in the front of the room, and then there's a whiteboard on the side of the room, and I list all these 5 laws of probability, and I even label them. I could have done that. Wouldn't that have been nice? Then you know what's going on. Are there more than 5 laws? Yeah, more than 5 laws. We will pretty much keep it simple in this class. We might learn a 6th later on. We'll see how it goes. But what I recommend is you copy these to another place. And just the fact that you copy them and organize them in one page helps you review, helps you study, helps you learn them. So that's my study advice. Alrighty, that should give everyone a chance to catch up. Let's erase this and start writing some other things. We've done coins, we've done dice, those are very common, and we'll do something else besides. In fact, let's do the traditional, a very traditional probability example. And this goes back several centuries. The history of probability, and we'll talk about it some. Well, it goes back into ancient times, right? Why? Because human beings had dice. Human beings like to gamble. The earliest dice were made out of the, if I can remember the name, I want to say astragalus. It's like the ankle bone of a small animal. And you can kind of roll them and different sides will come up, and it's kind of random. It's a convenient substitute if you don't have a store-bought die. Well, it's a convenient substitute if you've recently butchered a small animal and have its ankle bone. The history of gambling goes back, tens of thousands of years. Archaeologists have found dice that are very, very, very old, made out of bones like that. And so they had probably not a mathematical grounding in probability, but people had an intuitive feeling for, well, what's a good bet and what's not a good bet. So probability goes back itself thousands and thousands of years as a mathematical topic. It goes back probably, we have some interesting questions from the 12 and 1300s, and we will talk about some that were then solved in the 15 and 1600s, and that's kind of where modern stuff happens. By the 1700s, it was very firmly based in math, and there's still research being done now. But here's a problem that goes back quite a while. It's traditional because it has an urn in it, right? And the modern books don't use urns. They usually use cloth sacks. So if any of you had a little bit of probability in high school, it's the cloth sack problem. But the old problem had an urn in it. Fred has an urn. And what's an urn? It's a vase. It's not sealed off at the top, but it's narrower at the top. And you can put things in it and you can shake the urn up and that mixes them, it randomizes things. And then you can reach your hand in and the first thing you touch, you draw it out. And this is a very simple, very basic method to randomize things. And Fred's urn has 3 red balls in it, 2 red cubes, 5 yellow balls, and 2 yellow pyramids. I don't know where Fred gets all these little toys. Maybe he collects them. And then you can do all sorts of things. You know, what's the probability? Fred with these things and draws one out. So they're randomly mixed, and he reaches his hand in, and the first thing he touches, that's what he pulls out. And the idea is they're all kind of the same shape, and they're kind of the same weight. They're kind of the same size. And that's important because otherwise you can imagine if you shake the thing up to mix it, well, maybe the balls are heavier and they all sink to the bottom. Well, then Fred's not going to draw out a ball. He'll draw out a cube or a pyramid. And we don't want that to happen. We want it to be totally random. And that's the idea here. And as I say, most people don't have an urn anymore, but cloth bags. That's easier to understand. But I like the history, so I say the urn. What is the probability? What is the probability? He draws a ball. And this is pretty easy. The probability of drawing a ball, and here I'm using kind of a mixed formal and informal notation. The fact that I've used the P for probability and the parentheses for the argument, the thing we're finding the probability of, that's kind of formal, but I just wrote the word ball. I don't need to be really mathy about it and say, let A equal the event that Fred draws a ball. Then probability of A, P parenthesis, A parenthesis, that feels too formal to me. We don't need that. So we know it's action, and we know what is it? It's the number of balls. That's what we are interested in. How many ways could he draw a ball? Divided by how many ways could he draw anything? So the number of objects. And you say to yourself, well, how many balls are there? Well, there are 3 red balls, and there are 5 yellow balls, and total number of objects, I'm thinking 12 if I'm counting them right. 3 plus 2 plus 5 plus 2. And so this is 8/12. And if you're in 6th grade, then they make you reduce the fraction. And you're not in 6th grade, so I don't make you reduce fractions. There are certain reasons we kind of like having fractions. Yeah, I mean, you can reduce it and say, oh, it's 2/3. I don't know if that's necessarily a better thing. And I'll show you why in just a second. Let's do another example. What is the probability? So he puts the ball, whatever it is that he drew, he puts it back. He's starting with the full urn, and he shakes it up, and he reaches his hand in, and the first thing his fingers touch, he pulls that out. What's the probability that he draws well, let's do a red object, huh? And again, we're kind of reviewing. This should seem easy to you. The probability of red, we know it's a fraction. Probability is always a fraction. Well, it's the number of red objects. And how many things could he draw? That's the number of objects. And so how many red objects are there? There's 3 red balls, and there's 2 red cubes. And there are still 12 objects because we started over. And that's what a fraction again, 5/12. And so here's why I recommend not reducing. This is really, really simple because our denominators are 12. If I say which is more likely that he draws a ball or that he draws a red object, if I had reduced my first fraction, I would be comparing, well, the probability of one is 2/3 and the probability of the other is 5/12. And it would take you a minute. It would take you a little bit of thought. But if you say, which is more likely, 8/12 or 5/12, you say, well, 8's bigger, that's more likely. Yeah, he's going to draw a ball. That's the way to bet if this were a betting game. And so there's the idea there. Very traditional probability problem. And we just kind of did that for review, kind of for warm-up. So let's switch to playing cards, which are also very traditional in probability circumstances. Now, I recognize that some of my students, not all of my students, are experts in playing cards, and there are various reasons. You might be from a country. Some countries, I don't think they play cards as much. I mean, I guess this, I assume this because I've had students in the past who weren't familiar with cards. And it might be because what? You're a Nazarene, right? I had an aunt who was very religious, and I would see her play Uno, right? Because that's Uno. But I never saw a deck of cards in her house. And I don't think she ever played cards. And if you ask her about cards, she wouldn't be very familiar. So let's talk about playing cards for just a bit. A standard deck has 52 cards. And if you were that unlucky younger sibling who had a teasing older brother, you may have learned the game 52 pickup. The brother comes in and says, "Hey, you want to play a card game?" "Yeah, okay." Because, your older brother doesn't give you much attention. That's how older brothers are. He says, "You want to play 52 pickup?" And you say, "Oh, yeah, teach me." And then he throws the cards up in the air and they all fall on the floor. And he says, "There's 52, pick them up." Yeah. You know what my childhood was like. There you go, 52 pickup. So what do we have? We have 4 different suits in a deck of cards, 4 suits. And they have these traditional shapes. And if I'm clever about it, we can do these in color. Look at this. So there's a heart, and here's a diamond. You see why I teach math instead of art. We can switch to black. There are 2 black suits. There's clubs, and there are spades. Spades is kind of an upside down heart. So hearts, diamonds, clubs, and spades are the 4 suits. And then besides the 4 suits, there are 13 ranks. And those go from ace, which is the 1. So there's an A, and it's an ace. I'll write the word ace even. There's a 2, sometimes called a deuce, but sometimes I do that and sometimes I don't. And they go up to about 10 or so. And then you get face cards, the jack, the queen, the king. And these are the face cards because they have faces on them, right? So these are face cards. And that's what a deck of playing cards is like. So the way cards are used in probability is they're shuffled up. Fred shuffles a deck of cards and draws 1 card from the top. It's like he's dealing a deck of cards. And what we're interested in are some probabilities. What is the probability that he draws a face card? And if you are so inclined, you could work it ahead of me. I'm going to work it slower just because I'm explaining it. You could probably get it figured out before I write it all down. So what we will do is we'll say the probability of a face card, and here's my mix of formal and informal notations. We know that it's a fraction. It's always a fraction. In the numerator on the top, we say the number of face cards. How many ways can he draw a face card? Well, that would be how many are there. And then in the denominator on the bottom of the fraction, how many ways could something happen? That's just the number of cards. And so we look at this and we see that there are 1, 2, 3 face cards, and there are 4 suits. And so we will say 4 suits times 3. And how many cards are there? Well, we already know there are 52, and we get 12 over 52. 12 52nds as our fraction. And that's the probability that he draws a face card. And again, yes, you could reduce this, right? It's 1/4. We could even write that. Except it's not 1/4. It's 3/13. Yeah, 3/13. And let's just do that. Reducing, not required. And if we want to compare this to something else, which we will in a minute, it's probably easier if you don't reduce it. So let's do another one. So he shuffles up the deck. We draw, what's the probability that he draws something that is not a face card? So an ordinary card, not a face card. And here we go, probability of not a face card is, well, it's the number of cards that aren't face cards, divided by how many ways can things happen. That's the number of cards. And what we could do is we look at how many cards there are that aren't face cards. There's ace, call that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It seems there are 10. And again, there are 4 suits. And so this is very similar to what we just had. It's 4 times 10 divided by 52. And that comes to 40 50-seconds. And yeah, you could reduce it if you wanted to, right? It's going to be 10/13. And again, that's not required. I'm not sure why I did it. That should seem kind of easy, kind of ordinary. Usually about this point, when I'm doing this in a class, and the reason I refer to the class is I get more feedback in class, right? And I do like the feedback. All of your professors do like your feedback. That's something you can learn about college is professors typically love it when you ask questions. So in a class, do not be that shy person. Do raise your hand and ask questions, make comments. Usually about this time, if I'm doing this face-to-face, people say, well, okay, so you did this second problem, you got the answer, but isn't there a shortcut you could use? And yeah, there is in fact a shortcut. What I want you to notice is that, well, go back to law of probability number 2. The probability of the sample space is 1. And so if you think about it, you could get a face card, or you could get something that isn't a face card, and that's all the possibilities. The sample space, you're either going to get a face card or you're going to get a card that isn't a face card, and you're thinking those are the only choices. There's not some third thing that, oh, I got a card, it wasn't a face card, it wasn't not a face card, it was well, there isn't any other. It's either a face card or a face or not a face card. And we know from our second rule of probability, it's in your notes a page back, that the probability of the sample space is 1. That means all together, all of the cards, the face and the non-face, will add up to a probability of 1. Well, if your probability of everything happening is 1, and you subtract off the number of face cards, right, 12, then you'll get 40. And you can actually do that with the probability. If your probability of drawing a card is 1, you can subtract off the probability of drawing a face card, and you'll get the probability that it's not a face card. So let's write that out. There's some notation here. Here comes our third law of probability, so I'm writing it with a different color. Let me talk about math notation for a second. A lot of students don't like the math notation. And the way I explain it is I tell the students that among all the tribes of humankind, mathematicians are the, and I give the students an opportunity, and they say the smartest. And I think, well, thank you. Yeah, I'm a mathematician, so I appreciate that. It's probably not true. They're the, and they come up with all these different ideas. And they're always surprised how I end the sentence. Among all the tribes of humankind, mathematicians are the laziest. And the reason that's useful is if you come across a strange notation like this, then ask yourself, what is it the mathematicians are avoiding having to write? And if you think about it, well, here, I'll do a really, really quick one. I need a volunteer. Robert, you've got your mic on. Here's what I want you to do as fast as you can. In fact, I'll tell you, close your eyes, and then I'm going to have you do a little addition problem. It'll be up in the upper right-hand corner. So don't shout out the answer. Closed. We're adding up this stuff, and open your eyes. Tell me the answer. Yep, add those up as fast as you can.
Okay, 35.
Yeah, and what typically happens, and it's possible I'm wrong, but my guess is, and the rest of you, if we're in a face-to-face class, you'd all be staring at Robert, and he'd be sorry he volunteered, but I bet he didn't add up those numbers, right? You didn't add up those numbers. I really imagine.
Actually, I added them up because I thought you guys wanted me to add them up.
Oh, you did? Well, everyone else, every once in a while, I have someone who does actually add them up. 7 plus 7 is 14, plus 7 is 21, and 28, and 35. Okay, 35. They get the answer 35. But almost everyone in the class typically says, well, there's 5 of them, right? So 5 times 7 is 35. Well, what did you just do? You invented in your mind a notation that simplified this, and this is what I'm saying. Mathematicians are lazy, and so when you were in the third grade and you started learning multiplication, it was kind of, what? Why is this extra thing here? They're trying to simplify your life, so you don't have to add up all this stuff, and what's more, you don't have to write it all. And so this is the idea of mathematical notation, and I'll give you this just as an extra for the class. It kind of has nothing to do with what we're doing, but sometimes students get in math classes and it's frustrating. There's a little bit of a struggle because the notation seems complicated. And if you take a breath and back up and ask yourself, what are they trying not to write? They're trying not to write something longer.
Hey, I know what that notation means. Anything not A.
Yes.
If I remember right.
So, yes, is what they're trying to avoid is writing something that is not A. The technical term for this, and thank you, Robert, that's all I need from you right now. The technical term for this is the complement of A. And the unfortunate part is that there are several different ways that mathematicians choose to denote the complement of A. And so I've used A with a line over it. Sometimes they say A bar, but for this class, just say complement of A. I think one of the textbooks we use at this school uses an A with a little C up in the, it kind of looks like an exponent, C for complement. I like the bar. That's probably my favorite. So this word complement, let's talk about it for a second, because I love the etymology, and this will help you learn it and remember it. Notice it's spelled with an E and not an I. If you spell complement with an I, then you're saying, hey, your hair looks really nice today. Well, that's a compliment of A, right? You're saying something nice. You're complimenting the person. You're complimenting the event A. But this is spelled with an E, and what it comes from is a different word, Latin again. If you cover up the end of it, it looks like you're starting to say complete, and that's the idea, is the not A completes the A. It's everything else. And so you're thinking, oh yes, it's the whole sample space. Not A plus A, that's going to be everything. And so we have a simple formula for this. This is our third law of probability. The probability of not A, the complement of A, is 1 minus the probability of A. So there is our third law, and you could call this the law of complements if you wanted to give a name. And this is really, really nice, because if you say, well, what's the probability that Fred would draw a heart? And you think, well, hearts, how many hearts are there? There's 13 hearts. And how many cards are there? 52. There's 13 out of 52. That's his probability of drawing a heart. What's the probability that he draws something other than a heart? And you say, well, there's 13 of the diamonds, and then there's 13 of the clubs. So add that together, I'm 26. And then, well, that's a lot of work. If you're only trying to find the complement and you've only already found the probability of hearts, well, then you don't have to do much work at all to find the probability of something that's not a heart. You just subtract. And so it would go a lot quicker. And that's the point of these rules, by the way, is they make certain operations, certain calculations a lot faster, simpler. Okay, here we go. Fred rolls. So a six-sided die, and I mentioned six-sided because of things like Dungeons and Dragons. They have a lot of different sides of dice. There's actually a very strict way that dice are done, and I don't know if I've drawn it correctly. I don't know if any die actually looks like this, but it gives you a feel for what this is. So he rolls a six-sided die, and this is a great randomization device. It doesn't take fancy technology. You don't need electricity, and you can probably find a die in your home. Die, by the way, is the singular of dice, so you wouldn't say roll that one dice, you'd say roll that one die. Roll those two dice, and two is a little more complicated. We might do it later, but not today. He rolls a six-sided die. What's the probability he rolls an even number? And this isn't complicated, right? We're setting this up. The probability of an even, it's a fraction. Well, it's the number of even values. divided by the number of values. The number of ways the thing could happen divided by the number of ways anything could happen. And we might just list for ourselves, just to think about it, 2 and 4 and 6, I think those are the even values. And 1 and 3 and 5, well, they're not. And so how many are there? 1, 2, there's 3 of them. That's not hard. And how many sides? Well, it's a 6-sided die, so there you go. Well, that was easy. Let's do another one. Probability he rolls a 5. It could be he's playing some game, he's playing not Parcheesi, that uses 2 dice. Anyway, some game, and if he rolls a 5, then he wins, right? And if he doesn't roll a 5, then he doesn't. So here, the probability of rolling a 5 is the number of 5s. I think there's only one, divided by the number of values. And these are all kind of set up the same way. They're pretty easy. Okay, so what's this new thing then? So here comes our new thing that's even better, even more interesting, and it will lead to our next law of probability. It's a combination. What's the probability that he rolls an even number or 5? And the way you could set it up, this is the basic way to set it up, is we can say the probability of an even or a 5 is the number of values that are even or 5 divided by the number of values. And here I can list them out just to keep my head straight. Even values, there's a 2, there's a 4, you could get a 5, there's a 6. Look at this, I've even put them in order. So those are the possible values we're interested in. There are 4 of those. There are still 6 sides on the die, and so 4 out of 6. And this is the point at which a lot of students want to use a shortcut. And in fact, there is a shortcut. So here comes the shortcut. This is our 4th law of probability. So you can think of this as the OR rule, A or B. And what it's typically called in the math books is the addition rule, because it's the probability of A plus, there's the addition, the probability of B. So you could label this the addition rule if you wanted to refer to it that way. In the same way, number 3 was the complement rule. This is the addition rule. And this is a fine rule. I'm leaving a little bit of space because it doesn't always work. And so leave a little space in your notes because we'll have an if, and we'll fill this in a minute. Let's look at our counter example. I'm going to do it in red because it doesn't work. So here we're going to do the probability of, what's the probability that he rolls an even or a 5 or a 6? So here's even or 5 or 6. And we can set it up exactly the same way, right? We know it's a fraction, number of values, even or 5 or 6. And we think, wait. This is the slow way, right? Use the law. Okay, so what is it? It's the probability that it's even. We already know that. Plus the probability that it's a 5. We already know that, 1 out of 6. Plus the probability that it's a 6. Well, that's the same as the probability of a 5, right? There's 1 6. And so we've got 3 6 plus, it's a plus rule, it's an addition rule, plus 1/6 plus 1/6, and that equals 5/6. And the problem with this is that it is wrong. And you can all see why. Wrong. What was the explanation? We counted 6 twice. Because I counted it once when it was an even and once when it was a 6. And so there it is as an even, and there it is. This is too much. So it doesn't work. How can we fix it? we can put this restriction on our rule. The probability of A or B down here equals the probability of A plus the probability of B if A and B are disjoint events. And this word disjoint means, that's a little arrow. And let's just say they can't both happen. You could word it as they can't happen at the same time. They don't overlap. There's different ways you can express it. The fancy word in math is disjoint, right? The even numbers and the odd numbers are disjoint. There are no even numbers that are odds, and there are no odds that are evens. The even numbers and numbers divisible by 3, well, those aren't disjoint, because a number like 6, well, it's even and it's divisible by 3. Okay, so if A and B are disjoint events, that's our fourth law of probability. It's often called the addition rule because it has a plus sign in it. If you're interested in this probability and you're thinking, I could do this, this is covered in Math 123, which is Math in Modern Society. A lot of people take that as a terminal math class. It's the very last math class they take, and it covers all kinds of stuff, most of them meant to be useful in some way to an ordinary person. And so there's a bit of, kind of, it depends who you take it from. There's sometimes a flavor of algebra. You might do a few equations and you might do a little bit of graphing, but then you do a lot with personal finance. You'll figure out how to find how much a mortgage is and how much money you need to save for college or whatever it is. There's conversions between different units, right? Metric to feet and things like that. And then, anyway, it's an interesting class, and it has some probability and a little bit of statistics. And it goes a little farther than us in one way, and the way is they tell you what to do if A and B are not disjoint. And for our class, we're going to keep it simple. We don't need the extra stuff. We're just going to say, if A and B aren't disjoint, well, then, count it. Just do it the ordinary way. Don't use this law. But if they are disjoint, then, and if you do happen to already know these, and we did already know these, you can just take 3 6 and 1 6 and add them up and get 4 6. That would be faster than the way I did it by counting them out and listing them. I could just add them. So it's a shortcut if the rule applies. Let's do one more rule. Ed shuffles the deck. What's the probability that the card is a diamond? And we know how to do this. We set it up as a fraction. We're interested in diamonds. How many ways can he draw a diamond? That's how many there are. And how many ways could something happen? That's the number of cards. And we know both of these values from before. We know that there are 13 diamonds in a deck, ace through king, and there are 52 cards in a deck. And so the answer is 13 52nds. And yeah, you could reduce it to 1/4. Ed shuffles a deck of cards, draws one. What's the probability that it is a queen? And here it's the same sort of procedure. The probability of a queen will be the number of queens. I'm thinking there are 4 of them, divided by the number of cards. And so this is 4/52. Well, this is so much fun, we should do one more, shouldn't we? Yes, let's do one more. And then we will use our rule to find a shortcut for it. So Fred shuffles a deck and draws a card. What's the probability that it is the queen of diamonds? So now the probability of the queen of diamonds, see, I'm being a mathematician, using this simpler notation. And you can tell it's a diamond, right? Can you tell that's a diamond? I'm not sure. Instead of writing out queen of diamonds, I wrote Q and put a symbol. So what is this? It's a fraction. Queens of diamonds. That's what we're interested in. What's the anything that could happen? That's the number of cards. So there's one queen of diamonds, and there are 52 cards, and that's the probability. Let's see the shortcut. This is our 5th law of probability, and it's the last one we'll have for a while. The probability of both events happening, so A and B, equals the probability of A times the probability of B. And this is if, and we'll have an if here in a minute. We'll fill it in. So I want to work this as an example first, using the law of probability. Well, the probability that it's a queen of diamonds is the probability that it's a queen times the probability that it's a diamond. And we earlier found the probability of a queen. It's 13 over 52. And we earlier found the probability that it was a diamond. It was 4 over 52. And when we multiply those together, we get 13 times 4, that's 52, over 52 times 52. And I could multiply that, use a calculator, it comes out to 2,704. But what I want to do is I want to cancel this, right? And that's why I didn't bother multiplying it out, because I'm going to cancel it anyway. And what we notice is we got 152, 1 out of 52, using the shortcut, using the law of probability, the multiplication law, and that's the correct answer. So this is really, really good. This doesn't always work, though. And I don't know if I have the space. Let me squeeze it up. I can fit it. I'm going to use red again because this is all wrong, right? The probability that it's a diamond and it's red. Well, that's the probability that it's a diamond times the probability that it's red. And earlier we found the probability of a diamond. It's 13 over 52. And what's the probability that a card is red? Well, half the cards are red, so it's a half. And what do we get? We get 13 over 104. Well, that's all wrong, right? You could reduce that. You say it's 1 out of 8, and you think, no, wrong. So wrong. Make sure you put the words wrong in your notes if I do one of these counter examples, because if you don't, then later you'll look at it and you think, I don't understand this. Well, no, because it's wrong. I'm showing you the bad way. And here, what we're going to do down here in our rule, where I've left some space, we're going to add a condition, a restriction. So the probability of A and B is the probability of A times the probability of B. If A and B, so before, for rule 4, we said the OR rule works if the events are disjoint. Here we will say if A and B are independent events. So we defined disjoint as they don't overlap, they can't both happen at the same time. This definition is just a little longer, so I will type it. Okay, so let's unpack this. Two events are independent, and that's the word I'm defining here, independent. If knowledge of the occurrence of one event gives no additional information about the occurrence of the other event. And I really, really like this definition. I was talking about courses that have probability in it. I mentioned 123. The other course is 153, which is statistical reasoning. If you're going into the medical field, especially nursing, that might be a requirement. But of course, you're going to talk to your advisor before you sign up for any math class, because you don't want to sign up for the wrong one. They're all good. I teach them all, but you probably don't want to take the wrong one. Let me just say that. So why did I mention these courses? Because these courses, and this is my opinion, but I'm right about many things, and I'm right about this. The 123 book in particular defines independence wrong. And the 153 book defines it wrong and then has this extra blue box, and it says, some people, and here's an example, but it really explains it wrong. And we don't know yet as much as we will know later in week, let's see where it is, in week 11 and 12 and 13, we will do some work with philosophy. I like philosophy because it connects a lot of ideas, and that's the name of this class, Connecting with Ideas. And it will connect with what we're doing right now. But we don't know enough. What I'm saying here, and this will make sense in week 8, is that this definition is an epistemological definition rather than a metaphysical definition. And basically what I'm saying is two events are independent depending on what you know about them and not their actual cause. And so let me give you an example. The likelihood that it is raining and it is windy. And if I tell you, by the way, I already know that it is raining, does that tell you anything about the wind? And I don't know that it does. I mean, maybe you know more about meteorology and weather, but is there a rule that says, oh, if it's raining, then the wind is, and I don't know that rule. And so for me, at least, it would give me no extra knowledge if I knew that it was raining. Let's have a different example. What's the likelihood that it's raining and it's cloudy? And I tell you, by the way, I already know that it's raining. Well, then you know that it's cloudy, right? It gives you additional information to know that it's raining. Or take it the other way. What's the likelihood that it's raining and it's cloudy? And I tell you, hey, it's not cloudy. Well, then you know it's not raining because it doesn't rain if the sun is shining brightly and there are no clouds in the sky. It gives you some information about one event. Let me give a third example. This is one I've seen in textbooks, and it shows that this doesn't depend on the cause, it depends on the information. Because you can think of, well, rain, or clouds, I should say, clouds cause rain. And so if it's not cloudy, then you can't have rain. So here the example is, you walk in your house one evening, you unlock the door, and you flip the lights in your hallway as you're walking in, and nothing happens. It stays dark, and you go, oh, there's no light here in this hallway. And so you step into the kitchen and you flip the light switch, and nothing happens. And no one thinks to themselves, oh, the bulb burned out in the hallway, and that caused the bulb to burn out in the kitchen. No, people don't do that. They flip the one and they go, and they flip the other and they go, power is out. And so there's actually a third, there's an additional cause, there's an unrelated cause. It has nothing to do with your hallway light and has nothing to do with your kitchen light. There's something else that's causing both of those. And that's kind of a nice example where the knowledge, it would tell you something. If we wanted to, there is a way, there's a fancier version of this rule that would allow us, even if the events weren't independent, to use a version of this multiplication rule. But just like the rule number 4, the addition rule, we're not going to do that. We're not going to make this rule fancier. We might later, but not for now. So there you go. Those are 5 laws of probability. And think about these. You might think of examples